Hi everyone, my name is Miri Barak. I'm a professor at the Faculty of Education in Science and Technology. And in this session, we're going to discuss about visualization in science and engineering education. So one of our questions as educators is how can we explain an idea in a clear and a concise way, in a way in which we are going to explain a very complicated and abstract concept in science or in engineering that would allow our students to develop their mental models in a way as a scientist understands the concept. One of my examples is when researchers try to explain the concept of what is an atom. So if we're talking about Thomson in 1899, he perceived an atom as a positively charged sphere in which electrons are scattered within this sphere. Later on, Rutherford explained what an atom is in 1911 as a nucleus, and around it are negative particles that are called electrons. In 1913, Bohr discussed the idea of quantum orbits. Once again, the nucleus, positive nucleus inside, and then the electrons are circling it in quantum orbits. In 1926, Schrödinger developed his theory and the equation of the likelihood of finding an electron in a certain position. So we call it the quantum mechanical model. But as you can see, these are different types of evolution throughout the history of how atoms were depicted and described. And now, when we discuss the idea of an atom model, we're talking about electron cloud in which the nucleus includes protons, electrons, the protons and the neutrons are consisted of quarks in different positions, and this is how we now depict this concept, this quite abstract and complicated concept. So one of the ways in order for us as educators, science and engineering educators, to solve or to allow the communication of ideas, abstract ideas to our students, whether these ideas are in the macroscopic realm of atoms, molecules, or whether these ideas are in the spheres of our planet, is the use of visualization. So what are visualizations? They are visual presentations of information. They can be nonverbal or textual communication. They can be in the forms of tables, graphs, pictures, formulas, animations, or simulations. And it's actually a cognitive skill that we apply as researchers or as lecturers in order to lead our students to create their own mental models in their mind. So this concept, new concept, will be as close to the concept as researchers or experts see it in their own minds. When we talk about visualization, it's not a new idea. In Bhimbetka caves in India, we can see our prehistorical fathers and mothers painting, depicting daily life, hunting, childbirth, burials, and other situations where they want to convey different ideas and different actions, phenomena throughout their pictures, cave pictures. And this was dated already 30,000 years ago. And when we talk about today's visualization, we can define it in three areas. There are models, simulations, and animations. When we talk about models, we talk about textual models like the Schrödinger equation depicting the model of an atom. We talk about figures, pictures, drawings, and we talk about actual physical figures, such as, for example, this model, physical model of the diamond, carbon atoms forming a diamond. When we talk about simulations, we find physical simulations, and also now we have virtual simulations. And when we talk about animations, we usually mean virtual animations. So let's dwell in more deeply into each one of these types of visualization. When we talk about models, it's a means of presenting a scientific concept and processes throughout text, figures, or physical objects. And this is a beautiful, as you can see, picture of Linus Pauling, a Nobel Prize winner in 1954 for chemistry, Nobel Prize. And not only he depicts the equation of carbon molecules using the blackboard, he felt the need to present the concept, the spatial structures of carbon molecules using different physical models. Physical models include not only in the microsphere or realm, but also big systems such as the solar system, as you can see in this example. We have physical models of the human body, and we have, of course, physical models of the cell. So these are examples of models, physical models. When we talk about animation, we talk about a method in which pictures are manipulated to appear as moving images. It can be 2D pictures or 3D pictures, and it's actually what we call animation. The meaning is pictures in motion. So learners observe animated objects coming alive by accelerating static images. And you can see these 6 frames. When you look at these frames, these are static images of a round point, a red point. But when we move them fast, we can see that it turns into animated a picture of a bouncing ball. So this is another idea of animation. This is animation of animated drawing, the horse galloping, but we also evolved in taking pictures, photos, and now you can see an animated picture of photos running from frame 1 to frame 16. You can see the moving frames, and people could now understand better how horses gallop. Moving to simulations, this is another example of a horse, but this is an example of a simulation for a horse riding simulation. And this is a picture taken at the beginning of the 20th century of the Canadian police force. And this is a simulation of helping a policeman learn how to ride a horse. So simulations actually show a body or a phenomena, how it behaves under certain conditions. The learner is experiencing approximate imitation of the operation of the process or the system. So we move from the beginning of the 20th century to the 21st century, where we have airplanes, we have cars, so now we have also simulations of flying an airplane or driving a car. And simulations now are used in order for learning how to operate things, such as these examples, assessing performance, such as simulations in medical operations, and in many cases, predicting occurrence and response, such as earthquakes or material strengths. So using simulations help us save costs, enable proper planning, and sometimes save life. So when we want to compare between animation and simulation, it is important to note that in animations, learners are passively viewing a certain image, moving images, and in simulations, the learners have the ability to intervene and actually change the outcomes, do some manipulations. Following the development of graphical design, computing, and 3D capabilities, now we have the virtual reality technologies. The differences between animation and simulation are starting to become blurred. So let's see if you understood the differences. When you look at figure 1, which is a figure of a protein molecule, is it an animation or a simulation? What do you think? Looking at figure 2, this is a figure of Henry's law. Is it an animation or is it a simulation? Both are used for teaching sciences. What do you think? Let's move on to the next question. This figure C shows visualization of an engineering design. Is it a simulation or an animation? And figure D, a visualization of our Earth. Is it animation or simulation? If we want to summarize the idea of visualization in STEM education, STEM is an acronym for science, technology, engineering, and mathematics. We know that it's effective when it illustrates processes that do not appear in plain eyesight and are difficult for explanation. For example, if I would like to explain or to show you what is a pen, I would probably just show you this is a pen and show you more examples of different types of pens because you can see it in your eye. But if we're talking about abstract ideas, abstract concepts in science, in the microscopic realm or in the macroscopic realm, it's very difficult to explain, and then we do need to use visualization. Visualization has to be directly relating to the topic studies. It has to be well integrated into the science and engineering curriculum, and it has to encourage students' active and interactive connections in order to encourage collaborative learning. It has to, when we present the visualization, we have to state the analog. What does the roads mean? What does, in this example, okay, of the physical model of a diamond, what do the round or the black spheres represent? What do the metal road represent? So this is important to explain the analog and also explain the limitation. And one of the problems is that when we teach this way young students, many times when they're asked what is the color of a carbon atom, they usually say black. So no, carbon atoms are not black. This is only a physical model in order to represent something that we cannot see in the eye. So we need to be very careful about the analogs we're doing. When we look at the literature, study shows that visualization can increase the understanding of spatial structure of molecules. It can increase the understanding of algorithmic thinking in computer science and acquiring knowledge in mathematics. Also, studies show better understanding in biotechnology processes. However, it is advised not to use visualization when learners have the ability to visualize on their own the phenomena process independently. It might cause confusion or misconceptions if it's used in a way that is not promoting the understanding. And in these situations, visualization might inhibit learners from producing mental models and hinder their autonomous thinking. So just going back to the question as a summarization, we asked whether it's animation or simulation. So you can see that the protein molecule and the Earth turning around is considered as animation, and the other examples are examples of simulations. Students can manipulate the visualization on their own. So thank you for participating in this short session on visualization in science education. I'm Professor Miri Barak, and I hope to see you again in our next session. Thank you.